In this video, we present a new Distributed Moving Horizon Estimator designed to track a multi-vehicle system. The system under observation is composed of 5 vehicles controlled in a distributed fashion by a consensus formation controller. Vehicle 1 in the center is the leader. From the start point and driving within the road, they head towards the finish point. A sensor network composed of 12 cameras performs the distributed state estimation. Each camera is located aside from the road and can detect part of the vehicles when driving within the camera's field of view. Thanks to the fact that the moving horizon estimation paradigm involves a constrained optimization problem to solve online, we exploit the information of the field of view of each camera by using them as constraints for the state estimation problem. Indeed, this leads to better estimation accuracy. Moreover, the 12 cameras are connected to 12 Raspberry Pi, in which the distributed algorithm is implemented. The Robotic Operating System (ROS) framework performs the communication among sensors. In order to evaluate the algorithm's performance, it has been executed in 3 different scenarios. The first one is presented in this video. We use all the 12 cameras connected as shown in the figure. Let's start the experiment. At the top, we see 5 figures showing the actual positions of the vehicles, the estimated ones by the active sensors only, and measurements performed by these last ones. This figure shows the root mean square error averaged across the entire sensor network, representing a performance index of the estimation error accuracy. The computation time needed by each sensor to estimate the state of the system is shown here in this figure. The figure at the bottom right shows which vehicles are currently detected and by which cameras. For example, we now see that camera 5 detects all 5 vehicles. Since we are dealing with sporadic measurements, it means that the measurements are available at time instance a priori unknown. The accuracy of the estimation error rises and decreases over time, while the computation time is always around 6 milliseconds, much smaller than the sampling time of 0.5 seconds. The cameras are not always able to detect the QR code of the vehicles, which leads to having more sporadic measurements, as we can notice by the detections of camera 10. It is worth mentioning that both root mean square error and computation time are averaged among all the sensors. Indeed, in the end, when the vehicles reach the finish point, they are detected only by sensor 12. Despite this, the averaged error is decreasing. That is thanks to the consensus terms embodied in the distributed algorithm, which ensures the convergence of all observers' estimations.